So I'm going to give a somewhat broader perspective, going back some decades, like 50 years, and I don't think we need to go 50 years in the future, but I'll try to talk about what the key challenges are as it stems from the history as I've experienced it. So 1962, when I was 14, I wrote a letter to Marvin Minsky and Frank Rosenblatt at Cornell. The AI field was already bifurcated into the connectionist and symbolic schools. Minsky was recognized as the head of the symbolic school, though not widely known that he actually created the first neural net in the 1950s, but he was already skeptical of it by 1962. So both invited me to come up. Minsky spent all day with me as if he had nothing else to do. He was the consummate educator. He wasn't thrilled that I planned to go from there to Cornell to see Rosenblatt. And I then went to MIT. He became my mentor for over 50 years until his passing earlier this year. In recent years, he actually became more enamored with the connectionist school. The symbolic school had a problem which was not recognized in the early 60s, that of the complexity ceiling. You get to a point where the symbolic rules are so complex, you fix one thing and you break two other things. And unfortunately, that ceiling, that asymptote, is very often much too low to solve various problems. I went up to Cornell. The perceptron was getting a lot of excitement. This is probably before many of your time, but you probably have read about it. It had a camera, so I showed it some images in Courier 10, and it recognized them. I then took out a different type font and also Courier 10 in a different size. It didn't generalize. And he said, well, don't worry. We can feed the output of the perceptron. It was basically a single layer neural net with backpropagation to another perceptron, and then the output of that to another perceptron, and it will generalize as we add additional layers, and ultimately we'd be able to solve this problem. I said, oh, have you tried that? And he said, no, but it's high on our research agenda. So he died 9 years later, in 1971, never having tried that. Things didn't move quite as quickly back then as they do now. It would actually be decades before this intuition of Rosenblatt would be shown to be correct. So decades later, multi-layer neural nets were used. They really couldn't go much beyond 3 layers. They did generalize to some extent. But 5-6 years ago, the challenge to the AI field was you guys can't even tell the difference between a dog and a cat. And there was a problem going beyond 3 levels because the output of each layer has a error surface. That's a surface in a 1,000-dimensional space, and you need to keep that surface convex, otherwise the backpropagation gets stuck in a local minima, and it generally would asymptote also after about 3 levels, and 3 levels is not quite enough. That was a math problem. A group of mathematicians solved that, including one of my colleagues at Google, Jeff Hinton, and was able to transform the information after each level to keep the error surface convex. And now we could go to any number of levels. The difference between a dog and a cat is actually pretty subtle. It's at level 15, approximately. So now that we could go to a few dozen layers, these deep neural nets could tell the difference between a dog and a cat. We can now go to 100 levels. I read recently of 1,000-layer neural nets. At 100 layers, these, for example, image recognition programs can distinguish between thousands of categories at about human levels of performance, in some cases better. So this breakthrough, this math insight in being able to go beyond 3 layers to any number of layers is one of the factors responsible for this tremendous surge of confidence and interest and performance in AI. The other is the result of the law of accelerating returns, that we are getting exponentially more computation, data storage, actual data, and that along with the ability to actually do these deep neural nets is responsible for the tremendous progress that we've seen. By the way, the law, yesterday there were a few references to Moore's law. People still talk about Moore's law as if that's synonymous with the exponential progression in information technology. It's not. The law of accelerating returns, which basically says that the price performance of information technology, of which computation is one, progresses exponentially. That started decades before Gordon Moore was born. Moore's law, shrinking the size of features of transistors, was the fifth paradigm, not the first, to bring exponential growth to the price performance of computing. And that exponential progression also applies to other information technologies like communication or genetic sequencing and so on. For decades now, people are saying, but Moore's law is going to come to an end. And I'm saying, okay, but we'll go then to the sixth paradigm. That has happened. Moore's law, the shrinking of transistor feature sizes, has slowed down. The law of accelerating returns, which is the exponential progression of price performance computing, has not. We just updated our graphs through like last year, and that continues. We basically get twice as much computation each year for the same cost. We're now going to other paradigms, like starting to go in the third dimension, just lowering the cost of producing transistors and so on. So that has accounted for this tremendous progress we've seen, but there's still a few issues left. One is that you need a massive amount of data to do supervised learning. We're making some progress in unsupervised learning, but it's nothing like the fantastic progress we get with supervised learning. There's a motto in the connectionist field that life begins at 1 billion examples. And one of the reasons I'm at Google is we have 1 billion examples of some things, like images and like click data and translated language data and so on. But we don't have it on some other things. And humans can learn from less data. You hear something once or twice from your significant other or chairman of your department or your boss, and you can learn from that. At least some humans do that. But we don't always have 1 billion examples. So that's one weakness. Another is it can be very slow. LSTM, which is a very popular method of applying DNNs, deep neural nets, basically recomputes the whole net for each symbol in a sequence, and that can be very time-consuming. They don't explain themselves very well. We do discover at the deeper levels of a net some abstract features, the essence of a cow or a dog image, for example, but it's very often hard to find those explanations. They're not self-revealing. And there's another weakness, which is escaping me. So I've been interested in a somewhat different model, which is a hierarchy of sequential models, and I actually wrote about that 50 years ago in high school. The systems we developed for speech recognition in the 80s and 90s used hierarchical hidden Markov models, where the hidden Markov model was the sequential model. Unlike LSTM, it doesn't do long-term associations. It does local features, but that's actually what the brain is able to do. So I wrote a book, How to Create a Mind, came out in 2012. That's one of the things that got me recruited to Google. It talks about the evidence we have from the neuroscience field and also from observing human brains in action as to why the human neocortex is organized this way. For example, the European Brain Reverse Engineering Project has identified modules of about 100 neurons each that are basically repeated over and over again through the neocortex. And there's no plasticity within those 100 neuron modules. There's plasticity rewiring between the modules. A different project has actually found how the modules connect to each other. The vertical and horizontal connections are already there. They're made live, they're activated when the neocortex decides to connect this module to this module. The vertical and horizontal connections are already there. We actually have twice as many of those as a newborn as we do as an adult. The ones we never use die out. Um, and also we can observe human brains in action. These models are sequential and in an order, so we can recite the alphabet. If I ask you to recite the alphabet backwards, you can't do that unless you learn that as a new sequence. That's one of the reasons we use computers, is to make up for these fairly simple weaknesses of human intelligence. If I ask you to find some information, you might not be able to remember a particular name, because you have to actually be in the right branch of the right tree to retrieve information. The brain is not one big associative memory. If I give you a hint that helps you to put you on the right branch, then maybe you can remember it. So little hints like this, I make the case in How to Create a Mind that the neocortex is basically a big hierarchy of sequential models. The neocortex emerged 200 million years ago. It's able to learn new skills. It can learn from a small number of examples, as I mentioned. That's one of the benefits. Something happened 2 million years ago. If you remember, 2 million years ago, we were walking around. We didn't have these big foreheads. We had a slanted brow as primates. We then evolution created the frontal cortex, and we got these big foreheads. And up until recently, it was thought that it must be qualitatively different. It must be organized differently because it does different things. It turns out that it's really just an additional quantity of neocortex. This has also been shown in these brain reverse engineering projects. The layer that has the connections between the modules has somewhat more connections in the neocortex, but otherwise it's the same topology and organization of neurons. And it's basically learning a sequential model with local patterns, but not long-term patterns. The long-term relationships are learned by the hierarchy itself. So we got an additional quantity of neocortex. Now, what did we do with that? Well, we were already doing a very good job of being primates. So we put it at the top of the neocortical hierarchy. And as you go up the hierarchy, issues get more abstract and more interesting. At the bottom of the hierarchy, I can tell that that's a straight line. At the top of the hierarchy, I can tell that something is funny or beautiful. So that additional neocortex was the enabling factor for us to invent language and art and science and conferences, music. Every human culture we've ever discovered has music. It's actually the only universal art form. No other animal has music. We could argue about whale songs, but basically music came with that additional neocortex. The same with humor. Now that was a one-shot deal. We couldn't continue to increase the size of the neocortex. It already made childbirth challenging. Maybe there were a few humans that had more neocortex, but their offspring couldn't be born because their skulls were too big. So it was a one-shot deal, but it put it over that threshold so that we could invent, for example, technology, and that formed its own accelerating exponential process. So we're going to do it again. Because of the law of accelerating returns, this computer on my belt is billions of times more powerful per dollar than the computer I used when I went to MIT. I went to MIT because MIT was so advanced in the late 1960s it actually had a computer. This is millions of times less expensive. It's thousands of times more powerful. It's a several billion-fold increase in the price performance of computation. But that's actually not the most interesting thing about it. I can expand the capabilities of this thousands-fold. I can access thousands times more computation by connecting wirelessly to the cloud. Millions of times more in terms of accessing information. So a kid in Africa with her smartphone can access all of human knowledge with a few keystrokes. We can't do that yet directly from our neocortex. We do it indirectly through these devices. But in the future, once we develop strong AI, and I'm going to come back to talk about when I think that will happen, that will be in the cloud, and we will connect our neocortex to synthetic neocortex in the cloud. And just as this multiplies itself thousands or millions-fold by connecting wirelessly to similar computation in the cloud, we will do that with our neocortex, simulated neocortical modules. So I'm walking along in 2035, and I look up and say, oh, there's Max Tegmark. He's coming my way. I better think of something clever to say. I've got 2 seconds. My 300 million neocortical modules isn't going to cut it. I need 1 billion or 10 billion for 2 seconds. I'll be able to access that just the way your phone does that when it needs to translate something or do a search where it needs additional computation. So just as we did 2 million years ago, we will extend our neocortex and have additional quantity of neocortex. And just as we did 2 million years ago, we'll put it at the top of the neocortical hierarchy. So we will be more musical, we'll be funnier, we'll basically exemplify the things that we value. But unlike 2 million years ago, it won't be a one-shot deal. The cloud is subject to the law of accelerating returns. It is doubling in power every year as we speak. That will continue. So ultimately, the bulk of our thinking then will be a hybrid of biological and non-biological thinking. The non-biological part will be subject to the law of accelerating returns. It will expand without limit, ultimately will predominate. So let me come back and talk about when I think we will achieve human-level intelligence. At Google, I've been implementing my ideas of hierarchical sequential models. We're preparing some papers where we can talk in more detail about the actual results, but we are finding that it's orders of magnitude faster than LSTM. It can learn from much fewer examples. It can explain itself, and this is the other weakness that we found with LSTM is it can do certain semantic distinctions. I think if you can do language, you can do everything. I believe Turing's insight of basing a basic test of human intelligence based on language. I think language is Turing complete. We find that LSTM can't quite, it does do some semantic distinctions, but not others. We're finding more success with sequential hierarchical models. And so we're going to continue to move in that direction. So in terms of the future, I think there's general agreement that we're close to the hardware requirements of strong AI. We're there already in terms, but not at a reasonable cost. I think we'll be at a point where a human equivalent is about $1,000 in the early 2020s. In my view, that's 10 to the 14th calculations per second. I've got derivations of that in my book. Hans Moravec comes to the same conclusion using a whole different approach. There's some estimates that are 10 to the 16th, but the hardware problem is well in hand. The software problem is more complex. One of the points I make is that software progress is also exponential, and there's a lot of evidence of that. There was actually a study done by the White House Science Advisory Board on this issue. Have we gotten more benefit from hardware or software on a range of about 20 engineering problems? And they found that software had actually contributed more in terms of algorithmic improvements. That comes in fits and starts. It's not quite as steady as the law of accelerating returns applied to hardware. But I make the case that we will get there by 2029. So I've had that prediction going back to 1989. In my first book, Age of Intelligent Machines, I had that date within a decade or so. I said specifically 2029 in my 1999 book, Age of Spiritual Machines. Stanford had a conference about this startling prediction of AI experts, and the consensus then, we didn't have polling machines or online polls, there was a show of hands, but the consensus was 500 years. That was the median. Some people thought it would never happen. Recently, I've seen different analyses and polls of AI experts that range between 30 years and 50 years. So take 50 years. The reason for that advance, if you will, of bringing in the date is the law of accelerating returns. But in my view, it's not that people are really internalizing exponential growth. They're looking at the current rate of growth, saying, gee, at the current rate, well, in 1999, people said the current rate is going to take 500 years. Now people are looking at the current rate saying, yeah, at this rate of progress, we'll get there in 50 years. I agree with that, except that we're going to accelerate that rate of progress. That is not factored in. We're going to make 50 years of progress at today's rate in about 13 years. And people, linear thinking, linear expositions of the future, extrapolations, is really hardwired. So let me just, in the last minute, give a foolproof plan to keep AI beneficial. These futurist AI dystopian movies have, it's the AI versus the humans for control of humanity. And that's not a realistic vision, even of today. We don't have one or two AIs in the world. We have billions of AIs in the world. And that's going to get even more intimate. When I was at MIT, I had to take my bicycle across campus to get to the computer. Now we all carry them around. They're going to go inside our bodies and brains. They're going to keep us healthy. They're going to go inside our neocortex, connect to synthetic neocortex in the cloud. It's going to be a very intimate integration. So AI is not, it's not an invasion of intelligent machines from Mars. This is technology we create to extend ourselves. It's always been the role of technology. And we're going to continue to do that and intimately integrate with it. So here's the plan. I believe we have more of a consensus on values than we think. Things like democracy, liberty, tolerance, compassion. We could have a whole conference on that. That was not the case centuries ago. Even 1 century ago, there were only 5 democracies in the world. So the plan is, let's integrate these values, on which I believe we largely have a consensus, in our society today. This future society, the one that's dominated by AI, the one in which AI is intimately integrated with our existence, will emerge from today's society. And so if we embody those values today, the future society will also embody them. What could go wrong? Thank you.
Howdy, Richard Sutton. Yeah, I thank you for your presentation. I thought it was really clear, concisely making all these main points. But I wanted to ask you about, in your theory of how we're making the mind, the hierarchical sequential models. There doesn't seem to be an explicit role for goals and something like rewards or values in it. And can you sort of explain how, because we all care about the value part and the purposes, how does that fit in? It isn't normally part of what you'd call hidden Markov models, as you'd agree.
Well, I agree that it's not obvious that these hierarchical sequential models, which are basically pattern recognition models, would apply to things like planning and reasoning. I maintain that they do. A plan is a sequence of goals, and they each break down into sub-goals. And we're showing that we can actually do that kind of goal tracking and pursuit with an appropriate hierarchical model. I believe that's how we think. I've always thought that there was actually very little neuroscience evidence 50 years ago. There's actually quite a bit now. We can see in these modules that they have axons coming in from other modules, and that it is basically organized as a hierarchy of these modules, and the modules are doing sequential pattern recognition. And I talk about it in the book. It's a longer explanation, but basically plans are hierarchies. We want to accomplish certain things. Each of these are composed of sub-goals, and it all breaks down into a hierarchy of goals. Ultimately, we try to match reality to the goals and see where it differs, and then what we need to do to realize each sub-goal.
Okay, yeah. Jan Kuhn. Okay, Max tells me I'm supposed to stand up. So actually, Rosenblatt actually tried multiple layers. He just didn't have the learning algorithms for it. So there are several papers by him and his team with perceptron with 4 or 5 fixed layers followed by trainable layers, because he didn't have backprop. He didn't have backpropagation. He had least square, but I mean not least square, the perceptron algorithm, but he didn't have backprop. Backprop popped up in the control theorists figured it out in the 60s. It popped up in machine learning in the 70s, but nobody paid attention. And then it was popularized in the 80s. And there were neural nets with multiple layers already there. Convolutional nets in 1989 had 7, 8 layers. Recurrent nets that Jürgen and Joshua were working on had lots of layers, of course, because they were kind of unfolded in time. And so what happened in 2000, 10, 11, 12 is not a mathematical breakthrough, but a practical breakthrough. People realized they could run those things at a much bigger scale on GPUs with large training sets, and there were kind of a few conceptual ideas like using values instead of sigmoids. It doesn't make the cost function convex at all. It's still very non-convex, but there are properties that Joshua and I have been working on, mathematical theories that shows that this non-convexity is not a problem, actually. You don't get trapped in local minima. So, it's just kind of a slight historical correction. I'm channeling Jürgen here.
Well, okay. We could debate that. In my view, there was a mathematical issue that prevented us going beyond just a few layers. And once we could freely go to hundreds of layers, and it was not just GPUs, I think there was a mathematical issue that does have to do with the convexity of the error surface. But that's probably not of great interest to the group here. But
Jürgen, one sentence.
Just adding something to the